In this video we're going to discuss a specific counting situation in which we use what we call a permutation, okay? And so as kind of a lead into this, let's consider the following question, but the question is this: we say, in how many distinct ways could we rearrange the letters A, B, C, okay? And as a matter of fact, you know what, we could actually, if we took the time to do this, we could write this out. We could say, well, I suppose we could do A, B, C, or we could rearrange the B and the C, A, C, B, or we could start with B, we could say B, A, C, or BCA, or we could even start it with C and then say CAB or CBA. But the simple fact of the matter is, we could list all of these things out. It's just that in most instances, we don't have the time to list all possible cases for this. So what we're going to do is this: we're actually going to use the fundamental counting principle in order to do this counting situation, okay? And so the fundamental counting principle would say that if I have three letters, A, B, and C, and I wanted to put them in positions here where order actually matters, okay? And how many distinct ways could we rearrange these letters? The idea here was this: if I have three letters to choose from, in this first spot, then there are three different ways we could choose a letter to put in this spot. And as a matter of fact, we have three different ways to do it. Fundamental counting principle says that now that we know how many ways we could do the first thing, let's figure out how many ways we could do the second and third thing. We can just multiply this together and get all possible instances. It's just that in this case, that once I choose a letter, let's say I choose A to go in the first spot there, then I only have two choices left in terms of letters to put in the second spot. So we say, okay, well, once I've chosen a letter there, let's say I choose B for the second spot, then I only have one choice left over for this last spot. And so in other words, we get 3 times 2 times 1, and there are 6 possible ways. We should label this appropriately. So instead of ways, we could call it 6 possible outcomes for this thought experiment, okay? So what I want to know is this: it says, how would this situation be different if now we were asked to rearrange the letters A, B, C, and D, and how we could use our methods from the previous question to extend the situation. What we got now is a situation where we have 4 different letters, and we say, well, I've got 4 ways to choose a letter for the first spot, but then I only have 3 left to choose for the next spot, and 2 left to choose for this spot, and 1 left to choose for this spot. So this actual pattern that you see here, 4 times 3 times 2 until you get all the way down to 1, this has a name, okay, and there are 24 different outcomes for this here, but we usually use shorthand notation for this, and often you'll see it written this way: 4 with an exclamation point after it. And we're going to call this a factorial, okay? But before we get into factorials here in just a moment, these factorials right here, let's consider this a permutation. What is a permutation? We say when we reorder a set of n total objects. So for instance, in the first problem up here, we said that we had 3 total objects, and in the second instance, we had letters A through D. There are 4 total things for our n there. But when we reorder a set of n objects, we refer to it as a permutation, okay? So the idea here is this: permutation means this: order matters, okay? And this is basically the most important part of this video. Permutations means that you're rearranging things, or order matters. So the fundamental counting principle, we use that in either instance up here to determine the number of permutations of n total objects. And we said, for instance, if we rearrange the letters A, B, C, we took 3 times 2 times 1. We say in general the number of permutations or reorderings, I suppose you could say that's kind of a word, reorderings of n total things is going to be listed thusly, and I just got to get this letter G out of the way here, as n factorial, okay? And we read this as n factorial, and n factorial essentially means this: whatever integer value I give you here that's positive, we'll take n times 1 less than n times 2 less than n times keep doing this pattern until you get all the way down to 1, okay? So this factorial notation actually grows rather quickly here. We could say, in general, if somebody said how many ways exist to rearrange 7 letters, we could say that the total number of ways of rearranging this is just equal to 7 factorial. And we could say that's 7 times 6 times 5 times 4 times 3 times 2 times 1. And the fundamental counting principle would just back us up on this one, okay? So let's go ahead and take a look at values for factorials. It says, write out the following factorial values. Also use a calculator to help you find their values. The very first one I want to kind of communicate to my audience is this: 0 factorial by definition is equal to 1, okay? And this I'm going to write a little note here. Just by definition, kind of like anything to the 0 power is 1, this is one of those weird math facts, okay, that we accept that 0 factorial is equal to 1. Now 1 factorial, by definition, we would say that's 1 times, well, you would stop there, because remember, factorial says, let's take this number times 1 less than this number times 1 less than that number times 1 less than that number till you get all the way down to 1. Well, if you have 1 factorial, you are already there. Okay, so as far as 2 factorial is concerned, well, let's take a look at this. This would be 2 times 1, which is 2. How about 3 factorial? Well, 3 factorial would be 3 times 2 times 1. We've already seen this one here is 6. Okay, 4 factorial is 4 times 3 times 2 times 1, which we got earlier was 24 possible outcomes from this possible situation there. So now when we get to 5 factorial, what I want to do is this. Instead of writing out 5 times 4 times 3 times 2 times 1, what I want to point out is this. 5 factorial is really going to be 5 times 4 times 3 times 2 times 1, or in other words, 5 times 4 factorial, because 4 factorial, remember, means 4 times everything down to 1. And the only reason I say it's 5 times 4 factorial, it just means this. We could take 5 times what we just got on the last one here, which, by the way, 5 times 24 would give us our 5 factorial value, which is 120. Okay, so at this point what I want to do is I want to kind of make some inferences here, but basically this. First one is, if I said 6 factorial, it'd be the same thing as 6 times this 120, because remember, this 120 represents 5 factorial, and by definition 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is 5 factorial, okay? So in this case, we'd get 6 times this 120, gives us a 720. But what I want to do for the first time now is I want to actually get out our calculator. So we say 6 factorial. You'll notice that most calculators have a factorial key, and it has this little exclamation point after it. So if I type in 6 factorial, you'll notice that I got 720, which again, that 720 is just the same thing I would get by taking 6 times this last 5 factorial. And again, if we want 7 factorial, it'll be 7 times 6 factorial, or we could just grab a calculator and we could say, well, 7 factorial is 50, 40, and I do want to scribble all these down up to 10 factorial here. I want to show you how quickly factorial can grow. So 8 factorial, which is 8 times 7 times 6 times 5, 4, 3, 2, 1. 8 factorial is 40,320. So 4320. 9 factorial is going to be 9 times what we just got right there, but 9 factorial is 362,880. So we have 362,880. And then the simple fact of the matter is I can grab my calculator for 10 factorial, but we could also just take what we got right here times 10, which means we're just essentially going to add on a 0 to what we got prior to this. So we say there's the value for 10 factorial. So we say, what patterns do we notice here? Again, every factorial that we get is equal to that number times the factorial before it. But also this, we say that factorials, if I wanted to know how many different ways exist to rearrange n objects, and that's what it says here. It says the fundamental counting principle can be used to determine the number of permutations of n total objects. We say the total number of rearranging n distinct objects is always going to be just n factorial. So let's try to use this here alongside the fundamental counting principle to just kind of determine these easiest situations. But it says consider the following situations. We have 12 skiers that are competing in the final round of the Olympic freestyle skiing aerial competition, okay? So we'd say, well, what's our n value here? And remember, n represents the total number of objects that we have. So in this instance, it seems that we have n is equal to 12, all right? So what I want to know is this. In how many ways, how many different ways can the skiers finish the competition? And we say, assume there are no ties. So now, the important thing to notice here is that order actually matters. The order in which they finish matters. So if I have n total objects, there are 12 skiers here, and I say, how many ways could they finish? Instead of me having to say, well, there are 12 skiers, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Here's my 12. And then writing out 10 times, 12 times 11. Times 10, times 9, times 8, all the way down to 1. What we could really just say is this. There are 12 factorial ways or permutations that exist when we rearrange this. And as a matter of fact, 12 factorial, just to kind of show you how many different ways this could happen, there are a lot of ways that this can happen. So you can go ahead and write this down. We say 47900. So we have 479001600, and I believe that's what we have there. This many total outcomes exist for these skiers to finish this race, which is a lot. It's a lot. Okay. So on letter B here it says, in how many ways can 3 of the skiers finish first, second, and third to win the gold, silver, and bronze? And how is this different than the first situation? So now in this instance, I'm actually going to use the fundamental counting principle, which says, okay, we got gold, silver, and bronze. How many ways could this happen? Gold, silver, and bronze. We could say, well, there are 12 skiers that could potentially come in first place, but once somebody places first, then we only have 11 skiers left here. And then furthermore, we only have 10 skiers that could come in this third place spot. So since all we care about are gold, silver, and bronze, or first, second, and third, we could actually just multiply these out. We say 12 times 11 times 10, and there are this many. There are 1320 permutations of those 12 objects, but when we only consider 3 of those at a time. Okay. So now let's consider this. It says there's 10 golfers competing in a high school tournament. So in this case, we say n is 10. It says in how many different ways can all 10 of the golfers finish the tournament? Since we are rearranging all 10, we could really just say it's this. It's n factorial, or in this case, we say it's 10 factorial, okay? And just borrowing from what we know up top, we say 10 factorial is 36288 with 2 zeros after it, so we get 3628800. And this is how many different outcomes exist if we want to know how many different ways these 10 golfers can finish. And last but not least, it says, in how many different ways can only 4 of these golfers finish first, second, third, and fourth. So we say, well, now this is a little bit different from our last situation. Not a lot different, but since we're not rearranging all 10 of them, we're not going to write 10 factorial. We're actually going to need to list this out. We're going to say, here are our first, second, third, and fourth place golfers. We say 10 golfers could come in first, but then there are 9 that could come in second, 8 that could come in third, and then 7 that could come in last. So we could see here how this situation is very similar to the first 2 situations where we used a factorial. 10 times 9 times 8 times 7 equals 5040. Let's try this again. I just want to make sure 10 times 9 times 8 times 7 is indeed 5040. So we have 5,040 outcomes or ways that this could happen, that they could finish first, second, third, and fourth if there are 10 golfers to begin with. But you could see how there's a difference between rearranging all elements, in which we could just say it's that many factorial, and the second situation on each of these where we just said, maybe I have 12 skiers, but I only want to rearrange the first 3. Or maybe I have 10 golfers, but I only want to rearrange the first 4. So in our next video, we'll talk about permutations more generally, in which we're not rearranging all of the objects, but only a set number of those objects. Cheers.